Welcome to Solve First classes. Let us discuss something from Thermodynamics and Statistical Physics. A Carnot cycle operates on a working substance between two reservoirs at temperatures T1 and T2, where T1 is greater than T2. During each cycle, an amount of heat Q1 is extracted from the reservoir at T1 and amount of heat Q2 is delivered to the reservoir at T2. Which of the following statements is incorrect? Work done in one cycle is Q1 minus Q2. Q1 by Q1 is equal to Q2 by T2. Entropy of the hotter reservoir decreases. Entropy for the universe consisting of the working substance and the two reservoirs increases. A Carnot cycle operates on a working substance between two reservoirs at temperatures T1 and T2, where T1 is greater than T2. During each cycle, an amount of heat Q1 is extracted from the reservoir at T1 and an amount Q1 is delivered to the reservoir at T2. Which of the following statements is incorrect? Work done in one cycle is Q1 minus Q2. Q1 by T1 is equal to Q2 by T2. Entropy of the hotter reservoir decreases. Entropy of the for the universe consisting of the working of substance increases. Let us solve the problem. Solution. The efficiency of an engine is defined as the ratio of the network work done due to heat absorbed during one complete cycle efficiency is equal to useful work done heat absorbed upon heat absorbed, and that is equal to 1. After one complete cycle, the engine returns to its original state. Therefore, there will be no change in its internal energy. Therefore, returns to its original state. Therefore, there will be no change in its internal energy. There will be no change in its internal energy. That is delta U is equal to 0. From the first law we have delta U is equal to Q1 minus Q2 and minus W is equal to 0. So, or W is equal to Q1 minus Q2, where Q1 is the W is equal to Q1 minus Q2, where Q1 is the heat absorbed and Q2 is heat rejected, and W is the work done during one cycle, and W is work done during one cycle. Now from equations 1 and 2 we have from equations 1 and 2 we have and that is equal to 1 by Q2 by Q1. This equation shows that this N will always be less than unity. And therefore, if you draw the diagram like this, these are isotherms. Adiabatics. Then this is your going down is Q2. This is your VA. This is your VD. This is your VB. And this is your VC. Now this is your P and this is your V. Always be less than unity. Now let us go ahead and do something more. Let T1 and T2 be the temperatures of the heat reservoirs. Let temperature of the heat reservoirs such that the working substance say a gas is contained within a cylinder fitted with frictionless piston. Fitted with frictionless piston. We place the cylinder in the thermal contact. With hot reservoir and let the gas undergo a reversible isothermal expansion Let Q1 heat flow from the reservoir into the gas in the process. We indicate this change as A on the PV diagram figure. Work done W1 is equal to A to B PdV from the first law of thermodynamics. First law of thermodynamics, we know that for isothermal process, W1 is equal to Q1. Hence, using the equation of state for n mole of an ideal gas, we can write VA by VB dV by V. So NR T1 ln VB by VA is equal to 4. Now we have this as fourth equation where VB and VA, are volumes of the gas in states, are volumes of the gas in states B and A in B and A respectively. Point number 2. Next, what do we do is, next we thermally isolate the gas. Thermally isolate the gas and let it undergo reversible and let it undergo reversible adiabatic expansion. Reversible adiabatic expansion. The temperature falls from T1 to T2. The temperature of cold reservoir, the temperature of cold reservoir. This change is indicated as as B to C on PV diagram in figure. Work done is equal W2 will be equal to B to C PdV using the adiabatic relation PV to the power gamma is equal to K, we get W2 is equal to VB up to VC dV by V to the power gamma equal to K upon 1 minus gamma 1 by Vc gamma minus 1 upon 1 by Vb gamma minus 1, and that is equal to 1 by 1 minus gamma PCVC minus PBVB. So NR T1 minus T2 upon gamma minus 1. This using PCVC gamma is equal to K is equal to PB VB gamma. Now number third will be, now we place the cylinder in the thermal contact. Now we place the cylinder in thermal contact with cold reservoir with the cold reservoir at T2 and compress the gas isothermally and reversibly. Let Q2 heat be given up by the gas to the cold reservoir, this change is indicated as C to D. Work done is equal to W3 is equal to Q2. nRT2 ln VD by VC where VD and VC, C to D, where VD and VC are respectively the volumes of the gas, of the gas in states D and C. In states D and C, since VD is less than VC, equation 6 signifies that W3 is negative. Equation 6 signifies W3 is negative. That is work done on the gas. That on the gas. Now let us do the fourth point. The fourth point is the gas is again thermally isolated. The gas is again thermally isolated. Thermally isolated and compressed under reversible adiabatic conditions. And compressed under adiabatic conditions. Now till its original state is restored. Till its original state is restored. Obviously work done W4 is equal to D to A PdV is equal to NR gamma minus 1 T2 minus T1 minus W2. Since T2 is less than T1, W4 is negative quantity. Now the net effect of the cycle of this cycle is that we have extracted heat Q1, at T1 and put back Q2 at T2 and put back Q2 at T2. In the process, the total work done by the engine is total work done by the engine is W is equal to PdV W1 plus W2 W2 minus W3 minus W4, where the symbol means that the integral value, where the symbol, this one means that the integral value means that the integral value is taken around the cycle. From the diagram, it is clear that net work done by the engine is numerically equal to the area of the closed curve equal to area of the closed curve. In the PV diagram, figure, since W2 is equal to W4, we have W is equal to W1 minus W2, that is equal to NR T1 ln VB by VA minus NR T2 ln VD by VC, and that's your 8th equation. Then we have note that B and C lie on the same adiabatic curve. Then we have T1 VB, T2 VC. So T1 by T2 is equal to VC by BB whole to the power gamma minus 1. Similarly, for D and A, we can write T2 VD gamma minus 1 is equal to T1 VA gamma minus 1, or T1 by T2 is equal to VD by VA whole to the power gamma minus 1, and then whole to the power gamma minus 1. Then, or you can write like, VB by VA is equal to VC by VD. Using the resulting equation 8, W is equal to NR T1 minus T2 ln VB by VA. This is your equation x12. Now using 4 and 6, using 4 and 12, using 4 and 12, we can express the efficiency of heat engine. We can express the efficiency of heat engine in terms of temperatures within which it operates. Within which it operates. So therefore, efficiency is equal to W by Q1 is equal to NR by nRT1 T1 minus T2 ln VB by VA, and then you have here ln VB by VA. So if you will cancel all this, you will get T1 minus T2 by T1, and that is 1 minus T2 by T1 is the efficiency. That is your 13th equation is efficiency. This equation shows the efficiency of Carnot engine. Shows that efficiency of Carnot engine depends only on temperatures. Only upon temperatures of heat reservoirs of in fact, it is the temperature difference T1 minus T2 to T2. If two or more engines are working between the same high temperature reservoir, then the engine working over the largest temperature temperature difference has the maximum efficiency. maximum efficiency. On comparing equations, on comparing equations, 3 and 13, we further find that T1 by T2 is equal to Q1 by Q2. That is, for an ideal gas, the ratio also depends temperature T1 and T2. So for this question, the answer is option B is correct. Thank you so much for watching our video.